Namaste. Welcome to our channel Cupid Educational Services. I'm Pranesh, the founder of the channel and an IISc Bangalore alumnus. In this video, we are going to solve the physics MCQs from IISER Aptitude Test 2023. Let us begin with our first MCQ. A ball is thrown vertically upwards with an initial speed u from a height h above the ground. The ball eventually hits the ground with a speed v. The acceleration due to gravity is g and the air resistance is negligible. What is the average speed of the ball over its entire trajectory? U squared plus v squared upon 2 u plus v plus u by 2, gh by 2 u plus v, u squared plus gh upon 2 times u plus v. To solve this problem, we first draw the figure. So assume that this is our ground. The ball is being thrown vertically upwards with an initial speed u from a height h above the ground. Okay, so let this be the point of release of the ball. And the ball is being thrown with an initial speed u in this direction. Right, in this direction. Clearly, the ball speed is going to decrease, and after a ball reaches certain height, the speed will become 0, and then the ball begins its descent. Okay, it starts traveling downwards, and the moment it hits the ground, they are saying the ball eventually hits the ground with speed v. Okay, so this is going to be the speed v. Clearly, v is going to be greater than u, that's obvious. They want us to determine the average speed of the ball over its entire trajectory. This average must be averaged in time. Right, averaged in time. So let us first calculate the time of flight of this ball during its journey midway to the top and again falling on the ground. Okay, so it's a time of flight. Time of flight. Now, using the equation v equal to u plus at in usual notations, let's say the ball is being thrown upwards at t equal to 0, then the speed at which the ball reaches the maximum height, speed must be 0, initial speed is u, acceleration due to gravity is g, negative sign because this is a vector equation, and time. Okay, so what is the time? The time will be u by g. So this is only for the upward journey. Okay, this is only for the upward journey, and similarly you can find the time for the downward journey, and that time will be v by g. In that case, okay, let me use blue color for this. This is for the ascent. For the descent, the final speed is v. Okay, the final speed is v, the initial speed is 0, and therefore again the time of flight for the descent will be v by t. Okay, so we must now average our speed over this particular time of flight. Now here is the main thing. This is a result that you must know to solve this problem from definite integration. Okay, suppose there is a function f of x which is defined, let's say, on some closed interval ab, then the average value of the function over the domain is given by, in the numerator, definite integral of the function from a to b, and in the denominator it is the length of the interval, that is b minus a. Using this formula we have to find the average speed because speed is a function of time now. Okay, let us now divide our integral into two parts. Okay, let us now divide our integral into two parts because we already know the denominator. Denominator is nothing but the time of flight. Okay, let us first calculate the integral. Okay, integral of speed for the ascent or for the upward journey. Let's say for the upward journey. So how long is this upward journey going to last? This journey is going to last for time u by g, right? That's the time that we have calculated. The speed is going to be a decreasing function of time. Okay, please note that. speed will be the initial speed, that is u, minus gt. Okay, so this will be our integrand here. Please note this integrand is applicable only for the ascent part. That means the moment the ball is released, goes up, stops, momentarily stops. That is what we are going to consider now. Okay, u minus gt dt. Let's integrate this now. Ut minus g t squared by 2. Okay, let's now calculate the values of the function. Well, for the lower limit, we need not worry. For upper limit u by g, the first term will be u squared by g, and the second term will be here g by 2 into t squared. Okay, so it will be u squared by g squared. Okay, so what is this value now? I guess we can take, after cancelling g, we can take u squared by g common. 1 minus 1 upon 2 is 1 upon 2. So this will be u squared by 2g. Okay. Now let us calculate the integral of the speed for the downward journey. Okay. Integral of the speed for the downward journey. Okay. Equal to. Now, some of you might mistakenly take the limits right as u by g to u by g plus v by g. Well, that is the next interval of time. But in this case, you should make sure that the speed function is also appropriately shifted in time. Okay. So if you write your speed function using this formula that we have used, that v is equal to u plus gt, because the moment the particle begins its descent, the speed is again going to start increasing, right? And what is the function there? It will just be gt. The speed is going to increase linearly with initial speed being 0. So if you now take that as time, the integrand will be gt only, and the time will be from 0 to v by g. If you mistakenly take this as the function, okay, as the function to be integrated, please note, this function is not 0 at the lower limit, but at the lower limit our speed is 0. So this is wrong. Either you adjust the limits accordingly or you change the integrand. We chose the first. Okay, we adjust the limits according to our integrand. So this is right, this is wrong, this is right. Okay, so what is it going to be? There's only one term here, gt squared by 2. Let me directly substitute t as v by g. So g into t squared by 2, right? So v squared by 2 g squared. G will get cancelled. G will get cancelled. So I'll get v squared by 2g again. Right? Now what I am required to do is, I need to get back to this. Right? So we must add the two integrals. Okay. So on adding and dividing the sum by the time of flight, we shall get, okay, we shall get the average speed. Say average speed equal to. Acha, now what are the two integrals that we are adding? First one is this u squared by 2g, and the second one is v squared by 2g, right? So u squared by 2g plus v squared by 2g divided by the time of flight. The time of flight is u by g plus v by g. Okay, this is our time of flight. Okay, so it will be u squared plus v squared by 2 times u plus v, because g will get cancelled. Okay, now for those who got the idea immediately right after u squared by g, okay, because this function is symmetric, okay, well, for increasing function even or even for the decreasing function, because everything is positive, you can directly say u squared by 2g for the ascent. So for the descent, the integral has to be v squared by 2g. Okay, can just say that. And well, so that is the answer, u squared plus v squared by 2u plus v. Yes, so what is the right option? The right option is option A. Question 2. Two cubes A and B of same dimensions are made of different materials with the densities rho A and rho B respectively. Cube A floats in water with a fraction eta of its volume immersed. When cube B is placed on the top of cube A, it is found that cube A is just entirely immersed, while cube B is entirely above the surface of the water. What is the ratio of the densities rho B upon rho A? This problem is quite similar to a problem which was asked in the 2022 edition of the IISER Aptitude test, where there was water, a beaker containing water which was kept on the weighing machine, and then there was a cube which was either forcefully pushed inside the liquid or was held using a cable having some tension in it. Okay, there were two editions of it. I've uploaded solutions to both the versions. Please check out the link in the video description for that. Another buoyancy problem. This problem is actually simpler than that. Let's solve it. They're saying there are two cubes. There are two cubes, same dimensions, so same volume. Let us call that volume as V. They're made of different materials with densities rho A and rho B respectively. That's fine. Cube A floats in water with a fraction eta of its volume immersed. Okay. Now, if we decide to draw the free body diagram of cube A, okay, then its own weight is going to act downwards. Its own weight is going to act downwards. How much will it be? Density of block A, cube A, into its volume into acceleration due to gravity. This will be balanced by the buoyant force. What is the buoyant force? Buoyant force is going to act vertically upwards. This force is actually equal to the weight of the liquid, in this case water, displaced by the block, the immersed portion of the block. Now they are saying cup A floats in water with a fraction eta of its volume immersed. Okay, so eta V, this is the volume of water displaced. What is the mass of the water displaced? Into rho. Now let us take rho for density of water into G. Okay, that is FBD of cube A. Now they are same. Now if we draw the FBD of cube A plus B, okay, cube A plus B, then how much will be the total weight? Because they are of the same volume, the total downward force will be rho A plus rho B Vg. That is basically MAG plus MBG, right? In this case, what is the upward force? What is the buoyant force? They are saying when cube B is placed on the top of cube A, it is found that cube A is just entirely immersed while cube B is entirely above the surface of the water. So this time, the mass of the water displaced, or let me put it in this way, the volume of the water displaced is equal to volume of the block A or cube A. So the buoyant force will be rho V G. Correct? Now what we will do is, we know that these are two equilibrium situations, right? Both are equilibrium situations. In fact, both are static equilibrium situations. Correct? So, because we want the ratio rho B upon rho A, let us divide rho A plus rho B into Vg by rho A Vg. Now, because we have divided this, we must also divide the other two things. Understand that these two things are still equal to each other. That's why we are dividing rho A plus rho B into Vg by rho A into Vg. So what are we going to get? Rho Vg upon eta V rho G. Okay, now look at the terms that will get cancelled. Rho Vg entirely gets cancelled. So all we know is these two densities are smaller than that of water. Okay, even on this side, Vg will get cancelled. Now we can split, okay, the numerator on LHS. So it will be 1 plus the ratio that we want, rho B by rho A, equaling 1 over eta. Okay, so the ratio that we want, rho B by rho A, how much will that be? That will be 1 upon eta minus 1 or 1 minus eta by eta. Okay, you have to choose the options carefully. In this case, it is option A. Let's now solve question number 3 on ray optics. An object is placed in front of a convex lens. A real inverted image of double its size is formed. When the object is moved closer to the lens by a distance d, the image shifts away from the lens by a distance 8d from its previous position. What is the magnitude of the magnification in the final setup? 4, 1 upon 2, 8 and 16. To solve this problem, we will need two formulae from the ray optics and optical instruments chapter. The first formula being the formula for the magnification. In usual notations, it will be h prime by h or v by u. This is the first formula that we are going to use to solve this problem. And the second one will be, of course, the second one will be 1 upon v minus 1 upon u is equal to 1 upon f. In usual notations, f is the focal length. Now the second formula is important in solving the problem, although we do not know the focal length. And the significance of the second formula is that we have two different pairs for the image distance and object distance for the same lens. Okay, so second formula is important. One more thing before we actually begin the solution is that for a lens, when the image is real and inverted, the magnification is negative. Okay, magnification M is negative. They have said that a real inverted image of double its size is formed. So in the first case, M's value is negative 2. Okay, in the first case 1. Okay, so that will give us the first relation that is going to be helpful in solving the problem, and that is V by U is equal to negative 2. Okay. Secondly, if we now try to apply 1 upon V minus 1 upon U equation to our second case, what equation are we going to get? They're saying object is being moved closer to the lens. So this time the object distance is U plus D. Well, usually the object distance is negative, right? Because we always place the objects to the left of the mirror of the lens. But now we are taking this object closer to the lens, so we must add D to U. Okay, so this is the object distance, and what will be the image distance? The image is actually shifting away from the lens by a distance 8D from its previous position. Previous position was V. It is shifting away from the lens, right, by a distance 8D, so it will be V plus 8. Okay, now if we apply this formula to our new case, what are we going to get? 1 upon V plus 8D minus 1 upon U plus D is equal to 1 upon F. Okay, now because 1 upon F is the common factor, okay, because 1 upon F is the common factor, we are now going to equate the left hand sides of both these equations. This single step of equating the left hand sides is, according to me, the most crucial mathematical step to solve the problem. Okay? You may be knowing all the formulae, but well, at the end what matters is how you utilize them correctly in your situation. And I have found out at least that if you equate the two left sides of these two equations, it takes you to the solution. Acha, so let us now do that. 1 upon v plus 8d minus 1 upon u plus d is equal to 1 upon v minus 1 upon u. Before I do this step, I'll also tell you, well, what is the objective of this particular problem. They want us to determine the magnitude of the magnification in the final step, right? So m final, whatever it might be, by using the first formula v by u, in this case, what should it be? Should be v plus 8d upon u plus d. This is what we want, right? There are three things here, u, v and d. Okay, but we want the ratio v plus 8d upon u plus d. So we'll need another equation to find it, and that equation is m is equal to v by u, the first one, v by u is equal to negative 2, case 1. Okay. Now what I'm going to do is I'm going to send the term 1 upon v plus 8d to the other side. Okay, and I'm going to bring in the term negative 1 upon u to this side. Okay, so effectively we are doing 1 upon u minus 1 upon u plus d is equal to 1 upon v minus 1 upon v plus 8d. Take the LCM, u plus d minus u, so that will be d upon u into u plus d is equal to v plus 8d minus v, so that will effectively be 8d upon v into v plus 8d. Okay, d will get cancelled, and now, well, keep an eye on what we want. We want u plus 8d upon u plus, sorry, v plus 8d upon u plus d. Therefore v plus 8d, take that term to LHS, u plus d here, 8 times u by v, right? Now, do we know u by v? Yes, we know. U by v is 1 upon negative 2. U by v is 1 upon negative 2, right? So that is negative 4. We want the magnitude of the magnification, so that has to be 4. Okay, well, let me call this as equation 1, or let's say equation alpha, and this substitution of u by v as 1 upon negative 2 is from equation alpha, right? So that when you refer to the textual solution, you immediately understand how that negative 2 has come. Alright, that's question 3. MCQ number 4 on Doppler effect. The frequency of the whistle of a train moving with a constant speed is observed by a stationary detector on the platform to be nu1. The frequency of the same whistle is detected to be nu2 inside another train moving on a parallel track at a speed v towards the first train. If the speed of the sound in the air is taken to be v sound, what is the ratio v by v sound? Nu2 minus nu1 by nu1, nu2 minus nu1 by nu2, nu2 by nu1, and nu1 by nu2. To solve this problem, we recall the formula that we have studied in the Doppler effect, which says f prime is equal to f into v plus or minus vd upon v plus or minus vs. Okay, so in this case, what is f prime? F prime is the detected frequency. F prime is the detected frequency. F is the original frequency. V is the speed of sound. So let us use the convention here. V sound. Vd is the detector speed. And Vs is the source speed. Now, whenever the two things are approaching, either the detector or the source, one of them is going towards the other, moving towards the other, or they both are approaching towards each other, we have to consider the signs here in such a way that f prime is greater than f. Okay, that is the convention. Now, we have to apply the same formula to solve question number 4. We have to apply the same formula twice now. Okay, let us first consider the second case. Okay, let us first consider the second case, where they say that the frequency of the same whistle is detected to be nu2 inside another train moving on a parallel track at a speed v towards the first train. Okay, so in this case, if we decide to apply the formula, then nu2 will be equal to nu, that is the frequency of the whistle, into v sound. Now note that the detector is moving towards the source. Okay, the detector is moving towards the source, so we must consider it to be positive. And in this case, what is the detector speed? That is the speed of the second train, right? Speed v upon v sound minus v source. Okay, so let us now call it v train because we don't know about it. Acha. Now let us go to first case. The frequency of the whistle of a train moving with a constant speed is observed by a stationary detector. Okay, so when it comes to stationary detector, this term will now go to 0 because the detector is stationary. Okay, and they are saying that this is nu1, and in the denominator now it will be v sound plus or minus v train. Now I deliberately took the second case first. I'll now explain why I did that. Okay, suppose this is the platform. Okay, so the person who is observing the, or who is taking the note of the frequency, who is measuring the frequency, is standing on the platform. Okay, if we say that the first train, which is moving with speed v train, is approaching the platform, that's important. And if we now, or rather we have to now conclude that this is the direction of the second train, whose speed is given to be v. Okay, if you visualize this situation, then the ambiguity whether we should take it as plus v train or minus v train will get removed. The train is approaching, which means we have to now consider the negative sign because we want the frequency, observed frequency, to be increased, right? So let us now change this to v sound minus v2. Okay, and then we can divide nu2 by nu1. What are the terms that will get cancelled? Nu will get cancelled, so it will be v sound plus v, that is the speed of the second approaching train, upon now v sound minus v train, these two terms rather. Okay, let me use green color for that. These two terms, they will get cancelled, so it will be v sound plus v upon v sound. What ratio do we want? We want v by v sound, so let us subtract one. Okay, so if you subtract one, v sound will get cancelled, so it will just be v by v sound, and that will be nu2 minus nu1 by nu2. Okay, nu2 minus nu1 by nu2. Oh, sorry, let's see, nu2 minus nu1 upon nu1. Yeah, okay, this one. Okay, and well, let me check it again. Nu2 minus nu1, nu2 by nu1 minus 1, nu2 minus nu1 by nu1. Yes, nu2 minus nu1 by nu1. Yeah, that is option A. Okay, that is option A. Question 5. On current electricity, a current I flows through a cylindrical cable of length L and uniform cross-sectional area A. The power dissipated due to the current is P1. The cable is cut into two equal halves. If the cross-sectional area and the current flowing through the two halves remain unchanged, and the power dissipated in each half is P2, which of the following options is correct? To solve this problem, we will require two formulae. The first formula in usual notations is P is equal to I squared R. Power is equal to square of the current into resistance. The second formula is R equal to rho L upon A, where rho is resistivity, L is the length of the conductor, and A is the cross-sectional area of the conductor. Combining the two formulae, we can say P is equal to I squared into rho into L upon A. Okay, now let us apply this to our first case. Okay, case 1. They are saying that the power dissipated is P1. So P1 is equal to I squared into rho into capital L upon A. Okay, now let us consider the second case. Okay, they are saying if the cross-sectional area and the current through the two halves remain unchanged. So I squared is not changing. Material is anyways not going to change. And they are saying cross-sectional area doesn't change. So A remains unchanged. Okay, now they are saying the wire is being cut into two halves. So clearly this is going to be L by 2. Okay, L by 2. And this, okay, in each half is P2. The power dissipated in each half is P2. So if we take the length to be L by 2, P2 is the power dissipated in both the halves, right? Each. They want us to determine P2 in terms of P1. Now observe that I squared rho L by A is P1. I squared rho L by A is P1. Therefore P2 is equal to P1 into 1 upon 2, and that is option A. Question 6 on electrostatics. Particle A with charge Q and particle B with charge 2Q are fixed at positions RA bar and RB bar respectively. The force on A due to B is F bar BA, and that on B due to A is F bar AB. Which of the following options is correct? So basically we want to determine the forces and the vector relationship between the forces. Okay. Now please understand that according to Newton's third law of motion, every action has equal and opposite reaction, right? So both the forces must be of same magnitude, right? Both the forces must be of same magnitude. So clearly options C and D are gone because the magnitudes there are different. They're saying FAB's magnitude is twice FB's magnitude. Okay. Now we'll draw the figure. Suppose this is particle A, this is particle B. Okay. Now both are exerting a repulsive force on one another. Okay, both are exerting repulsive forces on one another because both bear positive charge. It's plus Q and this is plus 2Q. Okay, now let us show the directions. The relationship will immediately become clear to us. Okay. Force on A due to B. Okay, note that. Force on A due to B, it is going to be a repulsive force in the direction from A to B. Let me show it in red color. So this is going to be the force. Okay. This is going to be the force. Okay, F, B, A bar. Okay, similarly, reaction, its reaction will also be there. So now the force on B due to A. Okay, force on B due to A will be again repulsive. Okay. Yes. So this is the force on B due to A. Okay. Yeah. Now clearly you see that the two forces, if we consider them to be purely vectors, then F bar BA plus FAB bar should give us a null vector because they are along the same line, equal magnitude, opposite in direction. So that gives us FBA bar to be negative of FAB bar, right? FBA bar to be negative of FBA bar? Yeah, so that is option A. If AB bar is negative of FBA bar, that is as good as FBA bar being negative of FAB bar. Okay. Now you might wonder, how can they ask such a simple question? I'll tell you my guess. If I ask you, what is the electric field at B? Okay, electric field at B due to A. This electric field is actually, okay, this electric field here is actually 1 upon 4 pi epsilon naught plus Q upon R squared R cap. Okay, and if I ask you to determine the electric field at A due to B, it will be negative 1 upon 4 pi epsilon naught plus 2Q, okay, plus 2Q by R squared R cap. Which means if you decide to take a look at the strengths of the electric fields, not forces, okay, they're saying forces. In the problem they say force, okay, but here we are talking about fields. So field at B due to A is half of field at A due to B, because field charge B is greater in magnitude. Okay, directions are opposite for electric fields, but magnitudes, one is double the other. Magnitudes are not same. But while calculating the force at on a charge at a point, we multiply the field by that particular charge. That basically cancels out Q into 2Q and 2Q into Q. Okay, so for forces it's option A, and for for electric fields, I guess they have reversed the notation that we use conventionally, so I can pick the appropriate one, but please note that fields will not be same in magnitude as well as in directions. Okay, yes, let's now go to question 7. The magnetic flux phi b through a coil at a time t is given by phi b of t is equal to phi naught cos omega t, where 0 less than or equal to omega t less than or equal to pi, and phi naught is a non-zero constant. At what time is the magnitude of the induced EMF maximum? And we have got 4 options. This is another easy question in the paper. We have to use Lenz's law. Lenz's law, which states induced EMF E is negative of the derivative of the magnetic flux associated with a coil with respect to time. Okay, now because we want mod E, we will just take the derivative and put mod. We'll ignore the negative sign. Okay, so now phi b is phi naught cos omega t, so let us now differentiate that. Phi naught is a constant, and derivative of cos omega t is negative omega sin omega t. Okay, negative omega sin omega t, but again, because we are interested only in the magnitude part, it will be omega phi naught sin omega t, right? They want it to be maximum. So what is the maximum value of omega phi naught sin omega t in the range 0 to pi? Well, sin omega t is maximum when, in the range 0 to pi, when omega t is pi by 2, because that is when sin of omega t will be 1. Okay, now if omega t is pi by 2, t will be pi by 2 omega. Okay, t will be pi by 2 omega. There will be subsequent times where sin omega t is maximum, or the minimum will also do, which would mean that the polarity will be reversed, but the magnitude will still be maximum. Okay, so after every interval of pi, the value of sin omega t will reach to its maximum in magnitude, not in direction. Okay, fine. But I think as far as the problem is concerned, with the range of omega t restricted to 0 to pi, we have got the option that is A. Question 8 on semiconductor electronics. The intrinsic electron and hole concentrations of a silicon based intrinsic semiconductor are Ne0 and NH0 respectively. Upon doping with trivalent impurities, so it will be a p-type semiconductor, the respective carrier concentrations become Ne and NH. Which of the following options is true? NH greater than NH naught, Ne greater than Ne naught, Ne equal to NH, Ne naught and NH naught are independent of temperature. Clearly option D is not right. Why? Because if we increase the temperature, that basically translates to electrons in the valence shell having more energy, which means it is more likely their number will be more in the conduction band with increase in temperature. Okay, so that is not right, that Ne naught is independent of temperature. Okay, now let us come back to two very important equations that we have in our last chapter, semiconductor electronics. The first one is for intrinsic semiconductor, where the hole concentration is equal to the electron concentration. Okay, and the NCERT uses the term Ni, that is intrinsic charge carrier concentration, which is the same for holes as well as for electrons. Now if we dope that semiconductor with a trivalent impurity, that means p-type, what happens? We are now injecting more holes. Okay, we are now injecting more holes, and therefore the hole concentration will increase. The hole concentration will increase. In fact, NH now will be greater than NH naught. Had it been N-type, then Ne would have been greater than Ne naught. Okay, so we've got the answer. But I would also like to remind you that there is another relationship. Okay, what is that? That is NH into Ne is equal to Ni squared. Is equal to Ni squared. Okay, it is equal to Ni squared. So that Ni is actually the same as this one. Okay, so if one of them is increased, NH is increased, then automatically Ne will actually proportionately decrease. Okay, so question 8, option E. Question number 9, based on kinematics. The velocity v of t of a particle moving in one dimension is given by v of t is equal to alpha t when t lies between 0 and capital T by 3. It is equal to alpha into capital T by 3, a constant, when t is in between capital T by 3 and capital 2T by 3. And it is equal to alpha into capital T minus t, where t is in between 2 capital T by 3 and capital T, where alpha is a non-zero constant. What is the total displacement of the particle from time t equal to 0 to t equal to t? Okay, now the total displacement is basically a vector joining the initial position and the final position. Correct? We all know that. Displacement is basically change in position. So if this is the initial position of the particle and this is the final position of the particle, then no matter how the particle reached there, okay, any random path, displacement is always the vector joining initial and final positions. But if you observe the velocity profile of the particle, or VT diagram as we call it, then you will see that the magnitude, or basically velocity, never becomes negative. Okay, not magnitude, but what I want to say is the particle never reverses its direction. Okay, if we consider the VT diagram for this, okay, let's just consider it, VT diagram. Let me draw it here. If we consider the VT diagram of the particle, velocity v and time t, it's a 1D motion, right? So negative will mean the opposite direction. Now when t is equal to 0, velocity is equal to 0, correct? And then it increases linearly. Okay, it increases linearly. Okay, it increases linearly. Say something like this. Okay, this is the first third of the journey. Okay, this is from t equal to 0 to t equal to t by 3. Then for the same duration, the particle continues to move with constant speed, or constant velocity, I would say. Okay, it continues to move with constant velocity. So by the time it reaches to the 2/3 of its total journey time, okay, it would have traveled some distance with uniform velocity. And if you see now again, the acceleration here is same in magnitude as that in the first part if you take the derivative of this, but well, its sign will be negative because it is alpha capital T minus alpha small t, correct? Which means eventually the particle's velocity becomes 0. Okay, eventually the particle's velocity becomes 0. Right, the particle's velocity becomes 0. Okay, so this is t and this is 2t by 3. Right, so these are the velocity profiles during 0 to capital T. Acha. Now the point that I'm trying to bring now, well, because of all the discussion that we made, is that if displacement is the vector joining the initial and the final position, and in this case if the particle never reverses its direction, it means that the magnitude of the displacement, if you look at the options, it's only the magnitude that they want, is actually the total distance traveled. Usually that is not the case. Total distance traveled is actually equal to the magnitude of the displacement if and only if the particle never reverses its direction. Okay, so can we now calculate the total distance traveled? Of course we can. First of all, let's consider this phase of the particle's journey. It is a uniform velocity journey, uniform velocity phase. So the distance traveled will be velocity multiplied by the time taken. The time taken is t by 3. Okay, so alpha t by 3 into t by 3. Now everything is scalar now, so I'm using cos here, plus. Now observe that if the particle speeds up with some constant acceleration from 0 to some particular velocity, and if it decelerates in the same time with the same acceleration back to 0, the distance traveled will be the same. Imagine a ball being thrown upwards. When a ball is being thrown upwards, it goes to a height and it rests momentarily and falls back. The time taken for the upward journey and the downward journey same, and also the distance traveled in the upward direction and in the downward direction is same. That's exactly what is happening with our particle, okay, in 1D. Okay, alright, so we can now just calculate the distance traveled by the particle in the first phase from 0 to t by 3 and multiplied by 2. What is that distance? Use the equation s is equal to ut plus half at squared there. Okay, half at squared. Initial velocity is 0, right? Alpha t, t0, so that is 0. Plus half, what is the acceleration? Take the derivative of alpha t, so that with respect to t, so that will be alpha into t squared, so that will be t squared by 9. We must multiply this expression by 2, because when the particle is accelerating, it is going to travel this distance. When the particle is decelerating, even then it is going to travel the same distance, right? 2 will get cancelled. So the first term was anyways alpha t squared by 9, and so is the second term because of the 2 in the journey part and 2 in the derivation part, integration part actually. Okay, so it is 2 alpha t squared by 9, and it was only the matter of the constant, right? Alpha t squared was always going to be there in the options, so correct option is A. MCQ number 10 on units and dimensions. Two fixed point particles, each of charge plus q, are separated by a distance 2l. Another point charge plus q of mass m is oscillating about its equilibrium position as indicated in the figure below. The time period of oscillation is given by capital T is equal to 2 into pi raised to 3 by 2 into alpha into root of m by q. Given that epsilon naught is the permittivity of the free space, which of the following options is the dimensionally correct expression for alpha in SI units? Epsilon naught raised to half L raised to 3 by 2, epsilon naught raised to half L, epsilon naught raised to 3 by 2, L raised to 1 upon 2, epsilon naught raised to 3 by 2 into L. Okay. Well, although the situation is interesting, we will not analyze it. Rather, we will not analyze its dynamics. We are only happy with the dimensions part. Okay. So what are the dimensions of alpha? Rather, alpha itself. Okay, let's consider the dimensions. Dimensions of alpha. Dimensions of time, dimensions of charge upon dimensions of root m. Okay. So dimensions of time t, dimensions of charge. Charge is not fundamental quantity, right? Current is the fundamental quantity, which is rate of flow of charges. So we must multiply this by time. Okay, charge is current into time upon m raised to half. Okay, so effectively the dimensions are m raised to negative 1 upon 2, a to the power 1, t to the power 2. Now the options basically indicate that alpha does not have any dimension in length, right? L raised to 0 for alpha, but epsilon naught has an L dimension. Okay, so what we are now required to do is we are required to find out the length dimension or the power of the length dimension for epsilon naught and decide the correct option. Okay, so to begin with, let us recall the Coulomb's law. F is equal to 1 upon 4 pi epsilon naught q1 q2 upon r squared, right? So for epsilon naught, see, now we will write down only that part which we want. Q1, Q2 definitely not have any length dimension. R squared does have a length dimension, right? And what about F? Dimensions of force are M1, L1, T, negative 2. Okay, so the force term will, when it goes to the denominator of RHS, okay, it gets 1 L term. Okay, well, I'm sorry, this should be L squared, not L cube, because this is R squared. Okay, so epsilon naught has L's negative 3 power. Now to make the given quantity, to make the given quantity have 0 power in length, okay, we are first required to consider L raised to negative 3 by 2. Okay, and then we would like to add this, rather we would like to multiply this by 3 by 2. Well, we could have chosen any other number which would have made that. Let's say L raised to negative 3 raised to 1 upon k into L raised to 3 by k. We could have chosen any number, correct? That is not the thing. The thing is, in the options, what's the right number? In the options, the right number is 2. Epsilon naught raised to half L raised to 3 by 2, right? Epsilon naught raised to half means L raised to negative raised to half and L raised to 3 by 2. So that makes that option A. Okay, that makes it option A. Remember, for this to be dimensionally correct, okay, dimensionally correct, at least this part, okay, at least this part, 2 is there, okay, or many numbers are there. In fact, any number would do. And whether it indeed is equal to the dimension of alpha or not, that is decided by the other powers. And I think if you continue solving this, the other values of k will automatically get ruled out and only 2 will be the acceptable one. Alright, that is question 10. Question number 11 on current electricity. What is the effective resistance between A and B in the circuit shown below? 4R by 3, R by 3, 2R by 3 and R by 6, and we have this network from A to B. Okay, so first of all, let us notice if there exists any kind of symmetry of arrangement. Okay, so we have resistors R here, and we have resistors 3R, 3R and 3R here. Okay, and in between the two, in between them there exist two resistors 2R and 2R here. Okay, so clearly RRR, 3R, 3R, 3R and 2R, 2R. So there is some kind of cement, right? Especially if you look at the top branch and the bottom branch. Okay, if you look at the top branch and the bottom branch, we can definitely say that whatever incoming current there is, okay, let us say I, well, of course, the same current must leave here. But the thing is, if I assume that current in this particular branch is I1, the same current must be flowing in this branch as well, that is I2. I1. Okay, so I1 now. Let us assume that the current that flows here is I2. Okay, now consider the top junction. At this junction, we can assume that a branch of I1, a branch of I1 goes in this direction. Okay, let me choose a different color. Let me use green color now, but that's, don't get confused with the outer one. Okay, so okay, better let me use black color there. So this is I3, the one that is kind of coming downwards from that junction. So we must show an equivalent current or same current in the opposite direction here as well. So that is I3. Okay, now at this junction, which is the center of the square, I2 and the two I3s will merge together. Okay, so the current that is in this branch, okay, this branch of the circuit will be I2 plus 2I3. But at the same time, if you now look at the 3Rs here, the two 3Rs, okay, resistors, there by junction rule, this current, okay, will be I1 minus I3. This current here will be I1 minus I3. Same current will be here I1 minus I3. And when all the three currents through the 3Rs, they merge at B, we are going to get I1 minus I3 plus I2 plus 2I3 plus I1 minus I3. Okay, so what we effectively get is minus I3, 2I3 cancel, 2I1 plus I2. That is what the current we are going to get, 2I1 plus I2. Okay, and that is the current with which we started, 2I1 plus I2. Yes. Okay, so the network is complete. Now what we want basically is the equivalent resistance or the effective resistance, right? So how are we going to calculate it? Let us apply the loop rule. Okay, let us apply the loop rule for this loop, this triangular loop. Okay, let us now trace it in the clockwise direction. Okay, let's now trace it in the clockwise direction from A. So it will be negative I1R minus I3 into 2R, okay, plus I2 into R equal to 0. Okay, plus I2 into R equal to 0. And now what I'm going to do is I'm going to send I3 on the other side. Okay, so I3 into 2R, well, better we can drop R. Okay, we can drop R. So I3 into 2 is effectively I2 minus I1, right? Yes. Now let us consider another loop. Okay, let us this time consider this loop. Okay, let us trace it clockwise from B. Okay, let us now trace it clockwise from B. Okay, let me write it here. Loop rule. Okay, loop rule for that loop clockwise from B. Clockwise from B, right? Now this is against current, the 3R part, our direction, so it will be positive. So I2 plus 2I3 into 3R. Okay, again, okay, so that is also against current, the 2R part. So plus I3 into 2R, and now the minus part will come because now we are in the direction of the current, minus I1 minus I3 into 3R is equal to 0. Okay, is equal to 0. Now what? Let us continue simplifying, and as usual we are going to cancel R. Okay, so we will get 3I2 plus 6I3 plus 2I3 minus 3I1 plus 3I3 equal to 0. Okay, now as we did our part here, taking I3 on one side, we are going to do the same thing even for the next one. Okay, so let's keep I3 on this side. So 6I3, 2I3, 3I3. So how much is that? 6, 2, 3. So 11I3. Okay, 11I3 is equal to, now this is 3 times I1 minus I2. Okay, now if you observe the two equations that we have got here closely, okay, we are saying that I3 is negative 1 into I1 minus I2 by 2, right? From this, I3 is equal to negative of I1 minus I2 by 2. And here we are saying I3 is also equal to 3 by 11 times I1 minus I2, right? 3 by 11 times I1 minus I2. So what is that telling us? That is basically telling us that I1 must be equal to I2 because I3 has to be equal to 0. That's only solution that we have. Now the moment I3 becomes 0, we can actually remove that branch from the circuit, right? If I3, which was flowing through the 2R's part, we can remove it. And if I now remove it, it now becomes familiar with our series and parallel arrangements. But please note, we have not just said it's symmetrical. No, we have said it is symmetrical, we have utilized that fact, but ultimately we have used the Kirchhoff's loop rule or Kirchhoff's voltage law to arrive at the conclusion that we can actually remove them. Okay, yes, so this is now, okay, so it's now 3 resistors in parallel, right? 3 resistors in parallel. Which 3? This is A and this is P. Okay, these two, they constitute 4R. These two, the central ones, they constitute 4R, and these two, the bottom ones, they also constitute 4R. Okay, so what is the effective resistance? RAB, 3 resistors in parallel. So 1 upon 4R plus 1 upon 4R plus 1 upon 4R. Okay, so that will be 3 by 4R, and if you take the reciprocal, it will be 4R by 3, and that is option A. Okay, that is option A. Question number 12 on gravitation. Two spherical bodies A and B, each of mass capital M and radius capital R, are located such that their centers are apart by a distance of 4R as shown in the figure. An object C of mass m, small m, is thrown from surface of A directly towards the center of B with a speed v0 is equal to 2 times vmin, where vmin is the minimum speed needed for C to reach the surface of B. Given that g is the universal gravitational constant, how does the speed v of x of C change as a function of its distance x from the center of A? Okay, so we have got two spherical bodies A and B. Both have mass capital M, radius capital R, and the distance between their centers is 4R. Okay, the situation is that the body C is being projected radially outwards from A towards the center of B. Okay, so the trajectory of C is going to be in this line. Okay, now we are not interested in what might happen to C when it reaches P. We only want the velocity profile of the body C. Okay, now to get the velocity profile, first thing is that we must write down the acceleration that the body C experiences. Okay, assuming this direction, okay, assuming this direction to be positive, the acceleration vector A on C, okay, note that it is going to now have two components. First one will be the gravitational pull due to body A. So how much will that be? That will be negative gm, okay, negative gm upon x square, and then there will be gravitational pull by B, which will now be positive because our convention is left to right is positive. So plus gm upon 4r minus x square. Okay, note that they're measuring x from the center of A. Okay, they're measuring x from the center of A, so this is 4r minus x. Alright, now if we want the velocity profile, okay, well, how velocity varies with position, we must recall this particular formula for acceleration, which is v dv by dx, where v is the velocity and x is the position, right? So let us use that formula here. V dv by dx is equal to, okay, so let us take gm common, negative 1 upon x squared plus 1 upon, now let us write it as x minus 4r squared. That hardly makes any difference because we are squaring. Okay, now we will integrate this. Okay, on integrating, well, it is actually a variable separable differential equation, so if we integrate it, we're going to get v squared by 2 equal to gm 1 upon x minus 1 upon x minus 4r. Okay, well, we have used only one simple formula, that is integral of 1 upon x squared with respect to x is negative 1 upon x. Okay, let's not also forget that the problem that we are actually solving is a definite integration problem, but here we will first solve it as an indefinite integration problem. Okay, so we have to now add the constant of integration c to it. Acha. So this is our first part. In the first part, we have developed the expression for velocity, but that is not complete. That is not yet complete because we want to determine the value of the arbitrary constant c. Okay. Now note that gravitational force is a conservative force, right? If gravity is conservative. Okay, if gravity is conservative. Secondly, well, because it is conservative, we can apply energy conservation. And now we are going to the condition that they have given us in the problem regarding the velocity of projection. The velocity of projection, that is v naught, is a speed when x is equal to r, and that is 2 times v min. Okay, so at x equal to r, v is equal to v naught, which is 2 times v min. But what is v min here? V min is the minimum speed needed for C to reach the surface of P. Okay, V min is the minimum speed required at x equal to r. That is important. Okay, required at x equal to r to reach the other body B. Okay, so we will first try to determine the speed, okay, using this particular condition. Okay, now see, when v is equal to v min, okay, when v is equal to v min at x equal to r, what does that mean? Note that when the body has begun its journey from A to B, before the midway, Okay, let us now take this figure and try to analyze it better. Okay. Yeah. Note that suppose we have just projected the body C in the direction of B with the minimum speed. What is happening? Okay, when x is less than 2r. Okay, when x is less than 2r, that means it is still on the a side of the of the space. Okay, so when x is less than 2r, pull of A is stronger than pull of B. So clearly this implies that the body decelerates. That means C decelerates. Okay, its acceleration is negative. What does that mean? That means velocity of the body C decreases. Okay, velocity of body C decreases. Now note that we want this to continue to cross this particular plane, isn't it? Because if the body C fails to make it till that particular plane, it will be pulled back by A. Once it reaches that point and crosses it, then it is safe. The body B will now take care of it. Okay. So when we are projecting the body C from the surface of A with the minimum speed at x equal to 2r, Vc becomes 0. That's the condition. Okay, that's the condition. Now from this and the thing that we stated earlier, that if gravity is conservative, shall we now apply the energy conservation? Of course we can apply the energy conservation. So we'll say by energy conservation. Okay, by energy conservation at x equal to r and at x equal to 2r. Okay, now see, at x equal to 2r, the energy is going to be purely potential. Okay, so that is negative gmm upon r into 2, because the body is in the gravitational field of both the bodies A and B. Okay, and zero kinetic energy. This is equal to, now what is the potential energy of the body at x equal to r? At x equal to r, the potential energy will consist of two terms. Negative g, this should be 2r. Well, at 2r. Okay, we're calculating at 2. Okay. Now let's try to find the potential energy of this body C when it is on the surface of it. Okay, so what will it be? Negative gmm by r due to A plus negative gmm by 3r due to B plus half m v min squared. This is important because this is now going to give us the expression for v min. We will multiply it by 2, okay, and put it back in the answer of our integration problem. Okay, fine. So let's now proceed towards that. We can cancel m first. M. Okay, fine. So half v min squared is equal to, we can also cancel 2 and write negative gm by r outside. So it will be 1 here. This is negative gm upon r. This, when goes to the other side, becomes positive, but we have already taken the negative part there, so it will be minus 1. Okay, and then this will again be positive. Okay, positive gm by 3, but it will already be, well, we already taken negative outside, so it will be negative. Okay, so 1 minus 1, 0, and negative into negative positive, so it will be gm by 3r. Gm by 3r. And now this 2 goes here. This is v min squared, by the way. Okay, this is v min squared. Okay, now what do we have? At x equal to r given case, okay, v naught is 2 times v min. which means V naught squared will be 4 times V min squared. Now 4 times V min squared means 8 gm by 3. Okay, so we will now put this in the expression that we got here. Okay, because after all, well, this whole exercise is to determine the value of the arbitrary constant C, which will now take us to the answer. Okay, fine. So this is our indefinite integrations answer. Okay, this is our indefinite integral. Okay, V naught squared, that is okay. So now we are going to substitute x as r here and V naught squared or V squared as 8gm upon 3r. Okay, so V squared by 2, so that will be gm. Okay, 4gm by 3r, because of this 2 that will get cancelled, equal to gm into bracket 1 upon r minus 1 upon r minus 4r, that is negative 3r, so plus 3r. Okay, plus c, plus c. Now observe this. The box bracket, when simplified, actually gives us 4r by 3, right? Oh sorry, 4r by 3r squared, 4r by 3r squared. And if you cancel r, it will be 4 by 3r. Okay, now observe, LHS already consists of 4 by 3, or well, 4gm upon 3r. Okay, 4gm upon 3r, that means C is 0. Okay, C is 0, and that will take us to the final solution. Okay, how? Okay, so C is 0, we'll put it back here. Put it back. Okay, so V squared by 2, or V squared is equal to 2gm x minus 4r minus x upon x into x minus 4r, take LCM. Yeah, that's it, because C is 0 now. Okay, C is 0. Now how much will V be? Now observe, x and negative x will get cancelled. That negative 4r, okay, make it positive 4r. So effectively it will be root of 2gmr, that 4, write it outside, so that will become plus 2. And this x minus 4r will now become, it will become 4r minus x. Okay, it will become 4r minus x. Now you might ask, how did we do that? Or I mean, is it allowed? It's allowed because x is always going to be in the range 0 to 4r. So when you are taking the root, x minus 4r will be negative and its root will be imaginary. So before we take the root, we have absorbed the negative sign of 4r. Okay, we have absorbed that negative sign of 4r here by writing it as 4r minus x. Okay, now if we go back to the options, okay, well, sorry, that was the previous one. If we go back to the options here and try to find out which one of them matches with our answer, it will be option A. Okay, well, first of all, D and B are not right because they don't have the root sign for x. C is not right because it doesn't have the appropriate constant in the numerator, which is 2 root 2. Okay, so correct option is A. Question number 13 on atoms. Consider the Bohr model of an atom where an electron of charge negative e revolves around a nucleus of charge positive e in an orbit of radius r. The electron has an orbital angular momentum 2 into h upon 2 pi. Remember, h bar is actually h upon 2 pi. And the angular momentum of the electron is 2 into h upon 2 pi. If the nucleus had a charge plus 2e, what would have been the radius of the orbit of the electron with the same principal quantum number? R by 2, 2r, r and root of 2r. Now to solve this particular problem, we will first recall the formula that we have derived from the Bohr's postulates. Okay, and that formula is this. Rn is equal to n squared h squared epsilon naught upon pi mez e squared. Okay, in this formula, n is obviously the principal quantum number, h is the Planck's constant, epsilon naught permittivity of vacuum, pi constant, me mass of electron, e charge on electron, and z. This number is now important. What is z? Z is actually the atomic number from chemistry, which also equals the number of protons in the nucleus. Correct? Which is actually equal to number of protons in the nucleus. Now, please understand that there are two things that we need to consider here, or there are two things that may vary. What are they? They are n squared and z. Right? N squared and z. Now, what they are saying is same principal quantum number. They're saying principal quantum number does not change. The fact that the angular momentum of the electron, which they have given L, is 2 times h bar or 2 times h upon 2 pi, that is enough to provide us with the value of n. But even if we did not know this value, we were okay. Why? Because they're saying that what would have been the radius of the orbit of the electron with the same principal quantum number. So n is not going to change. N still remains the same. Okay. So although Rn depends on n squared and z, for us, what will it be? Rn will only be varying inversely with z. Correct? It will be varying inversely with z. Now, for the first case, okay, for the first case, how many electrons or how many protons, I would say, are there in the nucleus? There is only one. Okay, so for case 1, they are saying charge positive E. That means Z is equal to 1. And what is the thing for case 2? For case 2, the charge inside the nucleus becomes plus 2E. Correct? Plus 2E. That means Z becomes 2. Okay, now that should be it. We have the formula. Rn is inversely proportional to Z. So Rn old into Z old equals Rn new into Z new. Right? Now Rn old is R. Z old is 1. Rn new is what we want to determine. And Z is equal to 2. Which basically gives me Rn new as R into 1 by 2 or R by 2. Okay? R by 2, option A. That means the radius will actually get halved if there is an additional proton present inside the nucleus. Question number 14 on significant figures. A quantity has been measured to have a value of 0.00230 in some units. How many significant figures does the measured value have? 3542. Now, in order to solve this particular problem, you should know the rules of significant figures. Okay? If you apply them, then it turns out that these two zeros, which are to the right of the decimal point and to the left of 2, these are not significant. Okay? Secondly, the 0 which appears at the end, that is significant after the decimal point. And third thing, this number is actually less than 1. Okay, this number is actually less than 1. So 2, 3 and 0, these are significant figures. So their number is 3. So the correct option is A. Now for your reference, here is what NCERT book says. Chapter 2, 11th physics. All the non-zero digits are significant, so 2 and 3. If the number is less than 1, which is our case, the zeros on the right of the decimal point but to the left of the first non-zero digit are not significant. That means that the zeros between the decimal point and 2, they are not significant. Okay, so this is according to our second rule here. The trailing zeros in a number with a decimal point are significant. The trailing zeros, that means the zero here is significant, which means this particular value, it has 3 significant figures. Last problem, that is 15th from IISER Aptitude Test 2023 Physics on thermodynamics. Consider a Carnot heat engine operating between a heat reservoir at 600 Kelvin and an external atmosphere at 300 Kelvin. In one cycle, 1000 kilojoules of heat is extracted from the heat reservoir and the associated work is input to a reversible refrigerator that operates between 200 Kelvin and the same external atmosphere at 300 Kelvin. The refrigerator completes one cycle and releases heat into the atmosphere. How much heat is released into the atmosphere at the end of one cycle of the combined system? 2000, 2500, 1000 and 500 kilojoules. Okay, now please first understand what is meant by combined system. Our combined system consists of the heat engine and the Carnot refrigerator. Okay, so there are two, I would say two devices clubbed together, and we want to determine the combined heat rejected. We will first draw the energy flow diagrams. Okay, let's begin by drawing it for the heat engine. Source is at 600 Kelvin. Let Q1 be the heat extracted. So Q1 is 1000. They have given us. Okay, they have given us. Then this is our heat engine operating on a cycle. This is W, the work output, and this is Q2, right? And this is 300 Kelvin. Now, what is the efficiency formula for Carnot cycle? It is 1 minus T2 by T1, right? Well, we can actually derive it, but there's no need to derive it. If you know, you can very easily derive it. Okay, so the fact is the heats Q1 and Q2 are directly proportional to the temperatures. Okay, so Q1 is directly proportional to 600 Kelvin and Q2 is directly proportional to 300 Kelvin. Okay, that's it. Achha, so what is efficiency? 1 minus T2 300, T1 600. So 300 by 600 half, 1 minus half is half. So efficiency is half. That means Q1 will be equally split into Q2 and W. So W, which is eta times Q1, that will be 500 kilojoules, and Q2 will also be 500 kilojoules. Now remember, this Q2 is actually a contributor because that heat is being rejected. Okay, that heat is being rejected to what? To the atmosphere by the Carnot refrigerator. Okay, all right. So let us now draw the energy flow diagram for Carnot refrigerator. Now because its sink is at 300 Kelvin, let us now show it right here. Sink is 300, source is at 200 Kelvin, right? And this work here, this work is actually being supplied to the Carnot refrigerator. Okay. Assume that Q3 is the heat extracted from the sink and Q4 is the heat that is being given to the source. Okay, so what we now want to find is the value of Q4, knowing that both W and Q2 are 500 joules. Okay, so W is 500, well, not joules, sorry, kilojoules. Okay, now what is the formula for coefficient of performance for a Carnot refrigerator? Coefficient of performance is what you get, Q2, upon what you decide. That is, well, what you get upon what you supply. So that's W. Okay, and if you use the same formula in this case, okay, we have called it Q3, right? Yeah, Q3 is what we want and W is what we have given. Now we can easily write this as Q3 upon Q4 minus Q3, or it will eventually become T3 by T4 minus T3. Same formula or same proportionality relationship which we applied for heat engine. Same works for Carnot refrigerator also. Heat is directly proportional to absolute temperature. Okay, so what will be the coefficient of performance here? T3 is 200, right? And T4 is 300. 300 minus 200. So that will be 2. Coefficient of performance is 2. So Q3, which is COP times W, it will be 2 times 500. So Q3 will be 1000. But what is Q4? From the energy flow diagram, Q4 is Q3 plus W. Q3 is 1000. W is 500. So this will be 1500. And the contributors to heat being rejected to the surroundings are two, Q2 and Q4, isn't it? Q2 is the heat rejected by the engine, Q4 is the heat rejected by the Carnot refrigerator. Q2 plus Q4 makes it 2000 Kelvin. Sorry, kilojoules. Q4 plus Q2. 1500 from refrigerator, 500 from engine, so 2000 kilojoules per cycle. Okay, do we have that option? Of course, that is option A. So we have now successfully solved all 15 physics MCQs from IISER Aptitude Test 2023. I will be uploading a separate video on the detailed analysis and the weightage given to each and every section. The link to that video will be put in the video description. If you find my videos interesting, then please consider subscribing to my channel, Qubit Educational Services, and all the best to your future. Thanks for watching.